Green hydrogen is extracted from seawater by the new supersteel. Green hydrogen production could be revolutionized by a new type of stainless steel, which would lower the cost and increase the sustainability of clean energy. The invention addresses two significant issues with current water splitting systems: their high cost and lack of durability. This cutting-edge substance, known as stainless steel for hydrogen, or SSH2, was created by a university team. The study, which was headed by a professor, could soon serve as a foundation for hydrogen technologies of the future. Green hydrogen launching using SSH2. The stakes are really high. One of the most important instruments for reducing carbon emissions worldwide is green hydrogen, which is produced by splitting water using renewable electricity. However, it has not been able to scale up due to costly parts and short lifespans. By providing a more durable and cost-effective solution, SSH2 alters the equation. Parts of conventional electrolysis systems are frequently composed of titanium plated in platinum or gold, two valuable metals. The cost of production is increased by these materials. By matching titanium's corrosion resistance at a significantly cheaper cost, SSH2 delivers a breakthrough. Sequential dual-passivation is the technique that holds the key. This method includes manganese and chromium protective coatings. As a result, even in extreme circumstances, the material will not corrode. The general consensus is that manganese reduces stainless steel's ability to withstand corrosion. The discovery of manganese-based passivation is counterintuitive and cannot be explained by what is currently understood about corrosion research. They were persuaded, nevertheless, after a number of atomic-level data were shown. The crew was not only astonished but eager to take advantage of the mechanism. The potency of SSH2 in salty settings is what further increases its potential. It can function in seawater at voltages of up to 1,700 millivolts, which is significantly more than what ordinary stainless steel can withstand. This makes it possible to produce green hydrogen, clean energy straight from the water. Industrial operation and cost. The economic effects of SSH2 are significant. With SSH2, material cost for a typical 10 megawatt proton exchange membrane (PEM) electrolysis plant might be reduced by up to 40 times. The material is positioned as a game changer for industrial hydrogen production because of this cost decrease. There are still difficult jobs to complete as we move from experimental materials to actual products, including meshes and foams, for water electrolyzers. They have now taken a significant stride in the direction of industrialization. Together with a manufacturer, tons of SSH2-based wire have been manufactured. They are making progress in producing hydrogen from renewable sources using the more cost-effective SSH2. The material offers unparalleled corrosion resistance thanks to its dual passivation layers, especially the novel manganese-based layer. This guarantees robustness in challenging conditions, lowering maintenance expenses and raising the general effectiveness of systems for producing hydrogen. This innovation, known as stainless steel for hydrogen, offers a cost-effective and environmentally friendly way to produce green hydrogen. Expanding perspectives, green hydrogen in SSH2. SSH2 has the potential to transform a number of industries in addition to its direct effects on hydrogen production. Cost-effective materials like SSH2 make it possible to employ green hydrogen in a variety of industrial applications, such as ammonia production. Green hydrogen may be used to make ammonia, which is necessary for industrial chemicals and fertilizers, without emitting greenhouse gases. Oil refining. Cleaner fuels are produced through desulfurization, which is facilitated by hydrogen. Carbon footprints are reduced in this procedure by using green hydrogen. Steel making. Direct reduction of iron ore using hydrogen provides a sustainable substitute for conventional techniques while drastically reducing emissions. Methanol production. Methanol produced from green hydrogen is a multi-purpose fuel that promotes clean power generation and mobility. Green hydrogen is already being incorporated into the operations of Shell, Linde, and Bloom Energy, among other companies. For example, Linde creates cutting-edge hydrogen technology for a variety of markets, while Shell is working on massive green hydrogen projects around the world. By expanding the passive region of stainless steel to high potentials above water oxidation, the current sequential dual passivation technique makes them suitable anodic materials for the production of green hydrogen through water electrolysis. Sorting stainless steel technology obstacles. Long dependent on chromium, stainless steel's ability to withstand corrosion has been limited in highly oxidative settings. Even highly developed stainless steels, such as 254 SMO, are susceptible to transpassive corrosion. However, SSH2's dual-layer passivation method overcomes these obstacles. In situations with a lot of chloride ions, the manganese-based layer that forms on top of the chromium layer stops deterioration. This accomplishment expands on the history of cutting-edge materials research, which includes the development of ultra-strong supersteel in previous years and anti-COVID-19 stainless steel in 2021. The group's commitment demonstrates how material science may be used to solve pressing global issues. SSH2 is currently moving from the lab to the industrial setting. Now that tons of material have been manufactured, attention is turning to large-scale uses. The potential to reduce costs and emissions increases as businesses embrace this cutting-edge stainless steel, opening the door to a sustainable energy future. The creation of SSH2 emphasizes the value of scientific research while also supporting the worldwide movement toward decarbonization. Innovations like SSH2 are made feasible by questioning traditional wisdom and exploring novel concepts, which moves humanity closer to a cleaner, greener future. Researchers at the University of Hong Kong have developed a new stainless steel alloy called SSH2, stainless steel for hydrogen that is specially engineered to resist the highly corrosive conditions of seawater electrolysis. The team reports that the material can survive much higher anodic potentials in chloride-rich environments than conventional stainless steels, which potentially allows parts of an electrolyzer to be made from inexpensive steel rather than costly titanium or noble metal-coated components. Why this could be important for green hydrogen? Green hydrogen is made by splitting water into hydrogen and oxygen using electricity from renewable sources. Producing hydrogen at large scale requires very large electrolyzer systems and materials that tolerate long-term operation. Because seawater is vastly more abundant than fresh water, the ability to run electrolyzers directly on seawater, without expensive desalination, would greatly increase deployability, especially at coastal renewable sites. But seawater is chemically aggressive and rapidly damages many common materials. SSH2 is presented as a low-cost structural material that could reduce the capital cost of key electrolyzer parts by a large factor, which would lower the overall cost of electrolyzer systems and speed up adoption. How the steel works. Technical summary: conventional stainless steels rely on a thin chromium oxide passive film to block corrosion. In chloride-rich solutions such as seawater, that passive film can be penetrated or destabilized when the electrode is driven to high anodic potentials, causing pitting and rapid degradation. The SSH2 alloy is engineered to form a sequential dual-passivation structure. First, the usual chromium-based oxide layer forms, and then at higher potentials a secondary manganese-rich passive layer forms on top of the chromium layer. According to the researchers, this two-stage passivation greatly extends the potential window in which the steel remains stable, allowing the material to resist corrosion at anodic potentials reported up to about 1,700 MV in chloride media, well above the potentials where ordinary stainless steels typically fail. That electrochemistry-driven layering is the core material science innovation reported for SSH2. What SSH2 does not solve. Important caveats: SSH2 is a materials advance for structural and conductive parts that face chloride attack, but it is not a complete, system-level solution for direct seawater electrolysis by itself. Direct seawater electrolysis faces several other substantial technical challenges that materials improvements alone do not eliminate. These include the chlorine evolution reaction, CLR, at the anode, which competes with oxygen evolution and can produce chlorine gas or hypochlorite, precipitation and scaling, for example magnesium and calcium hydroxide carbonate deposits, membrane fouling and ion crossover in electrolyzer stacks, and long-term catalyst degradation and activity issues. System design, selective catalysts or protective anodes, pH control strategies, and membrane engineering will still be required to avoid side products, protect catalysts and membranes, and ensure safe, efficient, long-lived operation for commercial plants. In other words, SSH2 could lower one major cost and durability barrier, but practical direct seawater electrolyzers will require coordinated progress on multiple fronts. Practical next steps and likely timeline elements to move from promising alloy to widespread use. The following steps are typically required: long-duration field tests in real seawater and under cycling loads to confirm multi-year durability, fabrication of full components, meshes, foams, tanks and bipolar plates, and integration into complete cells and stacks, demonstration pilots at MW scale to validate system-level economics and maintenance needs, engineering to manage chlorine or form selective anode cell designs that suppress chlorine formation, and regulatory and safety testing, for example to evaluate chlorine hypochlorite risk and hydrogen embrittlement. The HKU team's report that industrial quantities of wire have already been produced is an encouraging sign of progress toward these steps, but large-scale commercial rollout will still require successful pilot demonstrations and supply chain scale-up. The SSH2 development is a notable materials breakthrough because it challenges conventional expectations about passivation chemistry and demonstrates a stainless steel that can remain stable in chloride media at much higher anodic potentials than usual. This advance could materially reduce the capital cost of electrolyzer structural components and make direct seawater electrolysis more economically attractive. Nevertheless, SSH2 addresses an important but specific technical barrier. System-level issues such as chlorine production, membrane and catalyst stability, and scaling must still be solved if direct seawater electrolysis is to become a reliable, large-scale commercial technology. Continued pilot demonstrations and multi-year stability tests will be the next essential milestones to watch. A breakthrough in green hydrogen production. The promise of SSH2 supersteel green hydrogen is widely regarded as one of the most promising clean energy carriers for a sustainable future. By splitting water into hydrogen and oxygen using electricity from renewable energy sources, green hydrogen offers a carbon-free fuel that can decarbonize industries, transportation, and energy systems. However, the large-scale production of green hydrogen faces significant technical and economic hurdles. Among the most pressing challenges are the high cost of electrolyzer systems and their reliance on scarce, corrosion-resistant materials such as titanium and precious metal coatings. A new breakthrough in materials science offers a transformative solution, a novel stainless steel alloy, known as SSH2, that enables efficient and cost-effective hydrogen production directly from seawater. The need for direct seawater electrolysis. Conventional water electrolysis typically relies on purified or desalinated water to avoid the corrosion and scaling problems associated with seawater. However, this approach adds significant cost and energy consumption, undermining the scalability of hydrogen production. Given that seawater constitutes over 97% of the planet's water supply, the ability to split seawater directly would be a game changer. Unfortunately, seawater contains high concentrations of chloride ions and other salts that aggressively corrode most metals and promote unwanted side reactions, such as chlorine gas formation. These challenges have historically limited electrolyzer components to expensive materials like titanium or nickel alloys, which dramatically increase capital costs. The development of SSH2 represents a major leap toward overcoming these limitations. By offering corrosion resistance on par with titanium at a fraction of the cost, this new material opens the door to cost-effective seawater electrolysis systems that could be deployed globally, especially in coastal regions rich in renewable energy. The science behind SSH2's dual-passivation strategy. Traditional stainless steels rely on a thin chromium oxide, Cr2O3, layer that passivates the metal surface and protects it from corrosion. While this passive layer is effective in mildly corrosive environments, it quickly breaks down in seawater, especially under the high voltages required for electrolysis. Researchers discovered a way to enhance this protection by creating a dual passivation system. In SSH2, the chromium oxide layer is complemented by an additional manganese-based passivation layer that forms when the steel is driven to high anodic potentials. This discovery is particularly remarkable because manganese was previously believed to reduce corrosion resistance in stainless steels. Instead, the researchers demonstrated that manganese plays a stabilizing role, allowing the steel to remain corrosion-resistant at electrode potentials of up to 1,700 millivolts in chloride-rich environments, far above the thresholds where conventional stainless steels fail. This breakthrough challenges long-standing assumptions in metallurgy and provides a blueprint for designing cost-effective, high-performance alloys for electrochemical systems. Performance advantages and cost savings. One of the most compelling aspects of SSH2 is its potential to drastically reduce the cost of hydrogen electrolyzers. In a typical 10 megawatt proton exchange membrane (PEM) electrolyzer, structural components made from corrosion-resistant alloys can represent over half of the total system cost, amounting to millions of dollars. By replacing expensive titanium and precious metal coatings with SSH2, the researchers estimate that the cost of structural materials could be reduced by up to 4-fold. The team has already scaled up production, manufacturing tons of SSH H2 wire in collaboration with industrial partners. These wires can be woven into meshes and foams for use in electrodes, bipolar plates, and other components that are critical to electrolyzer systems. This level of scalability is particularly significant because it demonstrates that H2 is not just a laboratory curiosity, but a commercially viable material that could be deployed rapidly. Industrial and environmental implications. If fully commercialized, H2 could accelerate the global shift toward green hydrogen by making large-scale electrolyzers both affordable and robust. This innovation has far-reaching implications for multiple industries, energy and transportation. Green hydrogen could replace fossil fuels in heavy industries, shipping, and aviation. Ammonia production. Hydrogen is a key feedstock in ammonia synthesis, which underpins global fertilizer production. Steel making. Hydrogen-based reduction of iron ore could replace carbon-intensive blast furnaces, dramatically reducing emissions. Synthetic fuels and chemicals. Hydrogen is essential for producing methanol, clean fuels, and sustainable chemicals. By making seawater a direct feedstock for hydrogen production, H2 also removes the water access constraint often cited as a barrier to global hydrogen deployment. Coastal regions, many of which have abundant renewable energy potential from wind and solar power, could become major hubs of hydrogen production without competing for freshwater resources. Remaining challenges. Although H2 represents a major step forward, direct seawater electrolysis still faces several technical challenges beyond corrosion resistance. The chlorine evolution reaction, CLR, competes with oxygen evolution, leading to chlorine gas production that must be carefully managed. Scaling and fouling from dissolved salts can also reduce system efficiency and longevity. Additionally, membrane durability, catalyst activity, and gas purity must be optimized for commercial applications. H2 solves a critical piece of the puzzle, the durability and cost of structural materials, but further research is needed to integrate this breakthrough into complete, safe, and efficient electrolyzer systems. A path forward. The research team's ability to scale H2 production suggests that the technology is poised for near-term pilot projects. The next steps will involve integrating H2 into electrolyzer designs, testing performance in long-term field trials, and addressing system-level issues like chlorine management and gas separation. If successful, H2 could catalyze a new era of affordable hydrogen infrastructure, enabling nations to decarbonize industries, produce carbon-neutral fuels, and transition to a renewable energy economy. The development of H2 stainless steel is a landmark achievement in the quest for affordable and sustainable hydrogen production. By leveraging a unique dual-passivation strategy, this alloy achieves exceptional corrosion resistance at a fraction of the cost of traditional materials, making direct seawater electrolysis feasible on a large scale. While technical hurdles remain, H2 represents a significant breakthrough that could reshape the economics of green hydrogen and accelerate the world's shift toward clean energy. Its potential impact extends far beyond energy production, influencing agriculture, steelmaking, transportation, and chemical manufacturing, all while reducing reliance on scarce freshwater resources. If adopted widely, H2 could become a cornerstone technology for building a decarbonized and sustainable future. The problem with current green hydrogen production: green hydrogen is typically produced through a process called water electrolysis, where electricity from renewable sources is used to split water into hydrogen and oxygen. However, traditional electrolysis systems usually require high-purity fresh water. If seawater is used directly, it rapidly corrodes standard materials like steel and even expensive metals, damaging the equipment and making the process economically unviable. To avoid this, companies often rely on costly components made from titanium coated with precious metals, like platinum or iridium, and/or pre-treat the seawater through desalination, which consumes additional energy and resources. Development of H2, a new type of stainless steel. To solve this problem, researchers at the University of Hong Kong developed a new stainless steel alloy called H2, stainless steel for hydrogen production. This new alloy is designed to directly withstand the harsh, corrosive environment of seawater, even under high-voltage electrolysis conditions. The steel was engineered using a unique manufacturing process known as sequential dual-passivation. This process involves two key steps that modify the steel surface. First, passivation layer, chromium-based. The surface of the steel is treated to form a thin, protective layer rich in chromium oxide. This layer enhances the steel's general corrosion resistance. Second, passivation layer, manganese-based. a second layer forms that contains manganese oxides, which further improves the steel's ability to resist corrosion in the highly oxidative environment created during seawater electrolysis. This is especially notable because, traditionally, manganese was thought to reduce corrosion resistance, but in this layered structure, manganese works synergistically with chromium. Together, these two layers create a durable, dual protection shield on the steel surface. Electrolysis process using SSH2. Once SSH2 is manufactured, it is used to fabricate parts of the proton exchange membrane, PEM, electrolyzer, which is one of the most efficient electrolysis systems. In this setup, electric current passes through the seawater, with the SSH2 acting as the anode-positive electrode, where the oxygen evolution reaction, OR, occurs. This reaction is usually very corrosive because it generates oxygen and creates highly oxidizing conditions, especially when seawater's chlorides are present. The SSH2, with its dual-layer protection, resists this corrosion even under high voltages, up to 1700 MV, allowing the electrolysis process to continue for extended periods without material degradation. The hydrogen gas produced at the cathode, negative electrode, can then be collected and stored for use as clean fuel. Direct seawater electrolysis. One of the key breakthroughs of SSH2 is that it allows direct electrolysis of seawater without any prior treatment like desalination or purification. This saves both energy and operational costs. Traditional systems either require desalinated water or rely on expensive materials that can handle seawater's corrosiveness. By using SSH2, the new system eliminates the need for such expensive steps. Manufacturing and scaling of SSH2. The researchers have already scaled the production of SSH2 at the industrial level. They have succeeded in producing tons of SSH2 in the form of wire mesh and porous foam. These forms are ideal for creating electrodes with high surface areas, which is crucial for improving electrolysis efficiency. This manufacturing process does not require rare or expensive elements like platinum, making SSH2 economically scalable for large hydrogen production plants. The estimated cost reduction for a typical 10 MW PEM electrolyzer could be up to 40 times lower compared to using titanium-based systems. Potential applications of the hydrogen produced. The green hydrogen produced from this process can be used in several important industrial sectors that are currently dependent on fossil fuels: ammonia production, for making fertilizers; oil refining, for upgrading fossil fuels into cleaner fuels; steel production. Hydrogen can replace coal and blast furnaces for making low-carbon steel; methanol synthesis, for making fuels and chemicals. By lowering the cost of green hydrogen, SSH2 technology could help decarbonize these industries much faster. Next steps for deployment. The research team has already begun collaborations with manufacturing partners to produce larger quantities of SSH2 materials for commercial electrolyzer systems. The next steps involve integrating SSH2 components into full-scale PEM electrolyzers, testing system performance and longevity in real-world industrial conditions, scaling up to serve large hydrogen production projects near coastal areas. The SSH2 super steel represents a major technological advance that enables low-cost, durable, and scalable hydrogen production directly from seawater. By solving corrosion challenges and reducing reliance on expensive materials, it has the potential to make green hydrogen more affordable and widespread, accelerating the global transition to clean energy. Are there prototype systems, and how can this be optimized for green energy deployment? There are already prototype materials and components made from SSH2, and they are being tested for integration into full proton exchange membrane, PEM, electrolyzer systems. Here's the current status of prototypes and deployment steps. Industrial scale production of SSH2 material. The research team has successfully produced tons of SSH2 in industrial settings, especially in forms like wire meshes and porous foams. These are key structural forms for making electrodes in electrolyzers. Component testing. They have tested lab-scale and pilot-scale electrode components in actual electrolysis conditions using real seawater, proving that SSH2 can resist corrosion and maintain performance under high voltages for extended periods. Electrolyzer integration. While a full commercial electrolyzer built entirely with SSH2 is not yet on the market, collaboration with manufacturing partners is underway to integrate SSH2 components into existing PEM electrolyzer designs. These pilot projects aim to replace conventional, expensive materials like titanium and platinum group metals with SSH2. Next stage: field testing and demonstration plants. The likely next step is the deployment of small demonstration plants, 100 kW to 1 MW scale, using SSH2 components for long-term field trials in coastal regions where direct seawater electrolysis is most valuable. How can this technology be optimized for green energy deployment? To optimize SSH2 and related systems for large-scale green hydrogen deployment, the following steps and improvements can be pursued. Integration with renewable energy sources, solar, wind, and offshore energy pairing. SSH2 electrolyzers can be co-located with offshore wind farms or solar farms near coastal areas, using the abundant renewable electricity and local seawater as inputs. Smart energy management systems use AI-based load management systems to balance renewable power fluctuations and optimize hydrogen production schedules. System design improvements. Advanced electrode geometry. The SSH2 foam and mesh can be further engineered into high surface area 3D electrode structures, increasing efficiency and current density. Enhanced catalysts. Though SSH2 addresses corrosion, optimizing low-cost, non-precious metal catalysts, e.g., nickel iron, cobalt manganese oxides, on top of SSH2 substrates could further improve hydrogen production efficiency. Thermal management. Incorporate waste heat recovery from the electrolysis process to improve overall energy efficiency. Direct seawater electrolysis optimization. Selective ion exchange membranes. Pair SSH2 with advanced ion selective membranes that allow proton conduction while blocking harmful chloride ions from reaching sensitive parts of the electrolyzer. Anti-fouling coatings and cleaning systems. To deal with biological growth, salt scaling, and sediment in real seawater, systems may need self-cleaning or anti-fouling features. System scaling and modularity. Modular stack design. Design electrolyzer stacks with interchangeable SSH2 electrodes for easy scaling from kW to GW scale projects. Containerized electrolyzer units. Develop portable, containerized hydrogen production systems that can be rapidly deployed at coastal renewable energy sites. Hydrogen storage and use integration. On-site hydrogen storage include compressed hydrogen tanks or explore hydrogen to ammonia conversion units on-site to store and transport hydrogen more easily. Local industrial hydrogen supply. Deploy the system near refineries, fertilizer plants, or steel production sites that can immediately use green hydrogen. Cost reduction through mass production. Industrial manufacturing partnerships. Accelerate partnerships with large steel producers and electrolyzer manufacturers to scale up SSH2 production. Standardization. Develop industry standards for SSH2-based electrolyzer components to simplify certification, installation, and maintenance. Life cycle assessment, LCA, and environmental impact analysis. Conduct full LCA studies to quantify the reduction in greenhouse gas emissions and water use compared to traditional desalination-based electrolysis systems. Optimize manufacturing and recycling processes for SSH2 materials to ensure circular economy principles are followed. By combining material innovation, SSH2, with advanced electrolyzer design, integration with renewables, smart control systems, and scaling manufacturing, this technology can enable low-cost, sustainable, and decentralized green hydrogen production directly from seawater. This could play a major role in global decarbonization, especially in coastal and island regions.